Hello, ladies and gentlemen. Welcome to Lecture 5. We're going to cover consciousness today. First thing that we'll do is distinguish between conscious and unconscious minds. Then we'll talk about what happens when we go to sleep. And then finally, we'll talk very briefly about some of the different drugs out there and how they affect brain function. Simply put, consciousness is our subjective awareness of who we are. Of our environment, how we interact with our environment. It's also how we remember our past, our emotions. Okay, so our consciousness is essentially ourselves, the selves that we're aware of. Now, no matter who you are, your consciousness is going to have 4 basic properties that are consistent with everyone else's. We all have intentionality. We all have some goal in mind. For example, these young people here are all in what appears to be a math class. They're in that math class likely because they're enrolled at a university. They're enrolled in the university because they want to get a job. They want a job so they can pay their bills, etc., etc. There's always a goal in mind. All right, you're watching this video because you're in this class. You're in this class again because you're enrolled in college, and you're in college because you want to get a job. Even on days though where you have nothing specific in mind, like on your day off, you might say, I'm just going to relax, I'll just chill. Well, that's still an intention. You intend to not mentally or physically tax yourself. There's still a goal there. All right, so any conscious being has a goal in mind. We also experience the world kind of as a single unified whole. Okay, so when you're sitting in class, or these folks here, they're sitting in their math class, the things that they hear and the things that they see aren't treated as separate items. If they're watching the professor work out a problem on the board, what they see and hear are treated as a part of the whole. In other words, how to perform this mathematical operation. All right, it's a single experience. What they're sensing isn't treated any different, though, from what's being created inside them. You know, any of their drives or emotions that they're feeling. That's not a completely separate version of them. That's all just the same them. We'll call this lady here Meg. If Meg's in a good mood today, well, her happiness isn't going to be treated as some weird event. She'll just think, I'm happy today, and I'm also in math class and taking notes, and all of this will be a unified Meg. Her memories as well. Meg today is really pretty much the same Meg as yesterday. It's not like she's a totally different person. Tomorrow she'll probably be very similar. Yeah, maybe she'll have a change in her moods, but she's going to take her memories as well and integrate that into her conscious awareness. She remembers when she was a kid. It's not like it was a completely different person. That was her. I mean, sure, you change over time, but it's still you. You know that it was you back then. And yeah, you've probably experienced some things, learned some things, and changed a bit in terms of your personality, but you still view it as you. You still create that unity. And then, of course, there's selectivity. Okay? First of all, we can't focus on everything, and in fact, we really choose to only focus on certain things. I've noticed some filtering going on in the classroom where, you know, people might, instead of listening to me, send text messages the entire time. That probably won't help you in the class, but that's your conscious decision. You've decided to selectively attend to your phone rather than the lecture. Or when you leave class, well, you're probably going to choose to pay attention to different things. You know, you're probably not going to attend to the same information outside of class as you would in. Okay, so you can choose what it is you're paying attention to. And if you're in a crowded or loud room like we're seeing here, this guy's having a great time, they all are. If you're at a party talking to somebody, there might be dozens or even more conversations going on at the same time, but you don't pay attention to all of them. You only pay attention to the one that you're engaged in. So that's what we call the cocktail party phenomenon. Even though there are other people talking and they're just as loud as the person you're talking to, you can understand their words. You can focus on what they're saying and kind of filter out all the noise. That doesn't mean that what other people are saying falls on deaf ears and is totally lost, because if someone says something that's particularly relevant to you, like your name, then you'll pick it up and switch your attention. So even though you're having a conversation with one person, not paying attention to others, if someone calls out your name, you can then recognize that and divert your attention. So your brain is still receiving the auditory input from everybody, but the conscious awareness that you construct is very selective. It's just the people you're talking to. And the final part of consciousness is the fact that it can change. We're not always the same person. You know, if you think about yourself when you were a kid, you probably had very different intentions, very, very different emotions. From day to day, we change. There might be some days where you might be moody, and maybe not on others. Even within the same day, when we leave the classroom, we change what our goal is. We're not always the same person, per se. We can change what our goal is. We can change what we're paying attention to. Our emotions change. We might change what memories we think of and how we view ourselves. All right, so consciousness is certainly not a rigid construction of the self. It can definitely change in the same day or over the course of your life. Now, consciousness is not an all or none event. Okay, there are some shades of gray. Most of us, I would think of as fully conscious. We know who we are. We can tell people about ourselves. But not everyone's so lucky. There's some gray areas of minimal consciousness that kind of blur the lines between unconscious and conscious. Sleep is kind of a minimal conscious state, but it's transient. So I'm going to focus on two sort of persistent states of minimal consciousness. One of them would be vegetative state. This is a coma, essentially. You're unresponsive. You seem, as far as we can tell, unaware of what's going on. It's typically caused by damage to the cortex. And we should recall from lecture 3 that the cortex is probably the most advanced part of the brain. It's involved in processing stimuli and creating plans and storing our long-term memories. So when you damage your cortex, no more processing of environmental stimuli, thus no more awareness of your surroundings. You can't formulate any plans or generate motor output, so no more responsiveness. Instead, all you are is just kind of running on auto here. Your autonomic nervous system still works, but your central nervous system is essentially shut down. This is sort of in contrast to locked-in syndrome. Locked-in syndrome is caused by subcortical damage, so those areas of the brain below the cortex. So these people are still aware. Their cortex isn't damaged, so they seem aware of their environment, but because of this subcortical damage, they're unable to move around or communicate this awareness very well. The only thing they can usually do is move their eyes, and that's how they communicate. So here's a fellow with locked-in syndrome. Let's have a quick look at it.
Mike has locked-in syndrome, but is able to communicate using his eyes.
Black, tail, black.
He looks at letters on a board, and Wendy has become expert at interpreting her husband's thoughts.
H for the black, D.
Given a little more time, Mike can also use a computerized voice system.
Can you explain what living with locked-in syndrome is like?
I think that you have to accept very quickly that you are totally dependent on others. This is perhaps the hardest thing to face. The realization doesn't hit you at first as you think you'll recover. Communication is very important because, without it, people tend to write you off.
And this is true. Communication is very important for our view of consciousness. If you're going to be fully conscious, it's not enough to just be aware of your surroundings. You have to actually be able to tell other people that. You know, how can we assume that somebody knows what's going on unless they can tell us? And so a fully conscious being is aware of their environment, and themselves, and then able to report their mental state. It's not only humans that are fully conscious. There are definitely other primates that seem fully conscious, and even other animals besides humans and primates seem conscious. You know, your pets are typically able to tell you kind of when they're happy or sad, and they seem aware of what's going on for the most part. Where they fail, though, is in the self-consciousness, their awareness of themselves as an individual and that they exist over time, and they had a past and they have a future and they can make those plans. Kind of one of the big tests that we have for self-consciousness is simply realizing that that's you in the mirror. That when you're moving about and that thing is mimicking you, well, that's because it's you. Now, we're not born with this ability. It's pretty early on in life that we become self-conscious. And this isn't reserved just for humans. Other primates seem capable of self-consciousness, but this is kind of where the lower animals kind of fall off. So humans and chimps are some of the animals that are self-conscious. But some dogs are going to struggle to identify themselves in a mirror even after they're fully developed. In general, the bigger and more complex the brain, the more complex the consciousness is. And this is simply because consciousness is the product of neural activity. We construct our awareness of the world when different parts of our brain become activated and communicate to one another. So if you have a simpler brain, if you have a simpler cortex, well, you're going to have much simpler consciousness. You might not be capable of self-consciousness, of realizing that you have existed across time and the little puppy version of you was actually you. Right? So dogs probably not so much, but humans definitely self-conscious. We have these big complicated brains. Now, one thing that you might want to ponder is whether or not your consciousness is fully in control of your actions. Right? I'd say certainly not. It's certainly not in full control. But what degree is it in control? We might think that for most of our problems or any decision we make, we first think about it, then we say, okay, I'd like to do that, and then we carry it out. Something as simple as choosing, do I press a button with my left finger or my right finger? We should be able to consciously choose this. And that should be the decision. It should be whenever we consciously decide, that's when it's made. I don't know if that's totally true, though. All right, we're going to walk through this experiment one step at a time here. What they are trying to state is that there's actually brain activity that precedes the conscious decision to carry out a behavior. And so there's something going on before we're consciously aware and the decision's already been made. All right, it's a grand claim. We'll see how the data actually look here, but let's run through this. This is the experimental setup. So what they did was take some participants, put them in an fMRI, and then ask them at any point you like, just you freely choose to press a button with your left index finger or to press another button with your right index finger. That's it. One of two options, press left or press right. While the patients were in the fMRI waiting to make their decision, they were shown a stream of letters that changed about every half second. So in this example, they started off with the letter K, then T, then D, then Q. At the letter V, right after Q, they actually pressed, let's say, the right button in this case. Once they made the press, then they show the participant another screen with a bunch of letters to say, all right, which one of these corresponds to when you made the decision? And in this case, the participant would say, I decided at the letter Q that I was going to press with my right finger, so they press the upper left, and that tells the researchers that the conscious decision to press with the right finger was made about 500 milliseconds before they carried out the action. And that seems about right. Once you decide to press a button, it's pretty quick to then press the button. But when was the decision really made? All right, first, something that's totally not surprising. Now remember, this is fMRI. We're going to measure brain activity, and we're going to represent it with these colored blobs. Okay, the top of that brain in the center, that's the front. The bottom is the back of the head. The left and right are the left and right sides. So the left motor cortex there, you can see its activity over time. So let's look at that graph on the far left. You'll notice a red vertical line. That is when the patient reported they made the conscious decision to press left or right. So the red vertical line in all these graphs we're going to see represents when the decision was made. And you can see after the decision was made, then the motor cortices became active. So if you're going to press with the right finger, well, then the left motor cortex should be activated. And you see in most trials here, they saw very robust activation of the left motor cortex when they were pressing right. And if they pressed with the left finger, well, then the right motor cortex became active. Now remember, we have those primary cortices as well as the secondary or associational cortices. On the bottom, we see a plot for the supplementar motor area, one of those secondary cortices. You can see that the activity of it comes on a little bit after the decision was made, but there's also some activity that precedes that, all right, by just a couple of seconds there. All right, I want you to remember that. We're going to come back to that in just a second. What this is showing you, though, is what were the regions that became active after the decision was made. Here's the real interesting data. What are the brain regions that became active before the decision was made, before there was the conscious decision to press left or right? And can those activities be used to predict whether we're going to go left or right? All right, let's start off at the top there. Look, we're at the frontal cortex. We should remember this is the region of the brain where we make our plans. And you'll see here that some activity has come on many seconds before that conscious decision to press the button. Now remember, fMRI has very poor temporal resolution, so the timing here shouldn't be taken as gospel. All right, by no means do we have very good accuracy in terms of time. Instead, we're very good with location. But even with that limitation, there's a somewhat better than chance predictive value depending on whether the lateral or medial portions of that frontal cortex became active. So in the more lateral regions, that could predict that the patient was going to press with their left finger about, let's say, 60% of the time. That sounds pretty good, but remember it's a one or the other option, so it's 50% at chance. So by no means are we reading minds here, but we can predict a little bit better than chance, and if you can take that with you to Vegas, well, you'll be a rich person. The counter to this would be the medial portions of that frontal cortex. The more medial regions were predictive of pressing right. So these activities came on before that of that secondary cortex. So here's the general idea. The frontal cortex kind of initiates a plan, and at this point we're not consciously aware of it. The secondary cortices then kind of check that plan. All right, let's go back and have a look. Okay, at our secondary motor cortex there, you can see that it's becoming active before the conscious decision, but not as early as the frontal portions of the cortex. So then we send that information from our secondary cortex to the motor cortex to actually carry out the movement. So that's the general flow. The front kind of initiates the plan. Secondary cortices check it and then tell the primary motor cortex, all right, press left or press right. Now what actually creates that conscious awareness is still an absolute unknown. It's a complete mystery. Different people have different ideas. Why is it that there's brain activity that precedes a conscious decision for several seconds when neurons are active on the millisecond time scale? All right, so this is still a big mystery in terms of what creates our conscious awareness. So our consciousness is a mystery, but so is our unconscious mind as well. There are a few different ideas floating around about how these two interact with one another, and we'll start off with Freud. This one's kind of out there. This is certainly an older idea. His whole thing was the dynamic unconscious. All right, there's kind of a war or a struggle between our conscious and unconscious minds. So in Freud's view, there were three parts of the mind. There was the id, the ego and the superego. So the ego would kind of be us, the us that we think of. For example, here's a nice old man, Steve. When you meet Steve, you're meeting his ego. There's Steve down there. Now, Steve also has the id and the superego. The id would be the more base, unconscious mind, kind of the dirty part of the brain where he has his hidden desires. And the superego would be Steve's sort of higher sense of morality and consciousness. And so in Freud's view, we have two different, essentially polar opposites for our conscious and unconscious mind. The conscious mind would be someone like Morgan Freeman. You might be wondering why he's there. Well, if you Google search wise old man, he's among the first to show up. So the conscious mind is kind of there to provide reason and to control the unconscious mind, which again has our more base desires. So the way that we create ourselves is by having the conscious mind constantly repress the unconscious and stay in control. And that's how we create Steve. This sounds a little far-fetched. More modern views instead state that the difference between our conscious and unconscious minds are simply that we're aware of the conscious mind and not the unconscious. This is the cognitive unconscious theory here. So these two work together now. They're not fighting each other. Your conscious mind is just what's going on in your cortex. What are you consciously aware of? Your unconscious mind. What's going on in subcortical areas? They're not totally different. You're not a different person under the surface there. You're probably very similar. These two work together. They're all Steve. Every one of these is Steve. One of them is the Steve that Steve's aware of, and the other one's the Steve that Steve isn't consciously aware of, but still kind of controls what Steve does. You know, for example, your cerebellum is really important for you to coordinate your movements. You're not consciously aware of what's going on in your cerebellum, but that doesn't mean that it's totally different from you. It doesn't mean that you're some kind of a pervert in your cerebellum. Of course, that's what Freud would kind of lead us to believe here. So nowadays, we just think of the conscious and the unconscious as two sides of the same coin. You know, whether you're looking at the heads or tails of a quarter, they're both 25 cents. Steve's conscious and unconscious mind are both Steve. One is just in the cortex, and one is outside of the cortex. All right, let's take a moment and see if we've gotten anything out of this. Pause the lecture, and we'll answer these in a bit. All right, consciousness, that is just your subjective awareness of yourself and your environment. You create who you are, and you're aware of what's going on around you. Now, your consciousness and anyone else's consciousness is going to have four basic properties. First is that intentionality. You have a goal in mind. You're coming to class for a reason. The second property would be unity. We don't view different events of our lives as completely separate. We just view them as different things that happen to us at different times. We don't view our different senses as completely different things. We put them all together. Everything we see, hear, smell, taste, and touch all at once are put together as a unified version of now. The third component would be selectivity. So we're able to decide what am I going to focus on. Can't focus on everything. You choose what to pay attention to. When you come to class, you can choose to pay attention to the lecture or other things. So we're able to select what enters our conscious mind. And then finally, there's transience. Our consciousness isn't always the same. Our moods change, our goals change, our views of ourselves change. What we pay attention to changes. That would be the transience. Vegetative states and locked-in syndrome are both types of minimal consciousness. Now, a vegetative state would be like a coma, where cortical damage causes us to lose all of our awareness and responsiveness. Locked-in syndrome is subcortical damage that causes us to maintain our awareness, but to lose the majority of our control over the body. So we can usually just move our eyes, but we're still aware of what's going on. We can communicate feelings still. We still experience emotions. We just have a very difficult time actually acting out our plans. Dynamic unconscious and cognitive unconscious. These are both views of how our conscious and unconscious minds interact with each other. But they are very different. So Freud's view of the dynamic unconscious is that the kind of base or poorly behaved unconscious mind needs to always be kept in check by our conscious mind. And what we create when we create ourselves is the product of repressing the unconscious mind to allow us to behave in a socially acceptable manner. Cognitive unconscious still has the two conscious and unconscious minds there, but they're not at war with one another. They work together. The cognitive mind is the product of cortical activity. The unconscious mind is the product of subcortical activity, and both of those work together. So when you make a plan in the cortex, in your conscious mind, well, then you're going to have the unconscious portions of the mind to actually massage and filter that plan to make sure that you carry out smooth actions. All right, let's talk a little bit about sleep here. Sleep is one of those minimally conscious states that we hit every single day. As we progress from awake to sleep and throughout the duration of our sleep, there are these characteristic patterns of brain activity that are observed. Because again, if we're going to alter our consciousness, the way that we do that is by altering brain activity. First, let's all get some terms under our cap here. Circadian rhythms. We all have these. Circadian rhythms are cyclic activities that occur with a rhythm of about once per day. So circa means around and dian means day. So things that we do about once a day. There are some hormonal fluctuations that occur on circadian intervals. Probably the best one, and the one we're going to talk about, would be sleep. About once a day, you're going to sleep. You can think of other things that you do about once a day. Well, those would be probably controlled by your circadian rhythms. So if we're going to have a rhythm, we're going to need some kind of a pacemaker. We're going to need some timekeeper. And we have that in the form of the suprachiasmatic nucleus. All right, the suprachiasmatic nucleus is a little region in the brain that acts as the body's internal clock. We're going to call the suprachiasmatic nucleus the SCN for the sake of time. There's a direct connection between your retina and the SCN. When it's light out, that inhibits the activity of the SCN because it says it's daytime. No more activity. When it's dark outside and there's no longer that inhibitory input from the retina, the SCN becomes active. So the suprachiasmatic nucleus then communicates with its targets. Only when it's dark though. So once it gets dark outside, the SCN becomes active and it will turn on some of its targets. One of those is a gland called the pineal gland. Remember that glands are going to release hormones. The hormones are going to circulate throughout our body. They're going to bind to their receptors and cause some change in cellular activity. Well, the pineal gland is going to release the hormone melatonin. If you've ever taken melatonin, you'll know that it does make you sleepy. So what melatonin is going to do, when it's dark, SCN gets active, turns on the pineal gland releases melatonin, melatonin circulates throughout our body and kind of slows down our metabolism and shuts down the activity in the brain. Sort of. Okay, that's a gross oversimplification. There's quite a bit more going on than that, but for now, we'll keep it there. If it's dark, the retina doesn't inhibit the SCN, it becomes active, turns on the pineal gland, and then melatonin makes us sleepy. Once it's light again, our retina turns off the SCN, pineal gland gets turned off, no more melatonin, we can wake. All right, that's how we'll keep it for now. Now, sleep, that's the focus. All right, sleep is a minimally conscious state. Okay, we're not fully aware of what's going on. We're not responsive to everything. Okay, so we're not fully conscious when we're asleep. So there's some change then in brain activity since there's a change in our consciousness. This is measured using EEG. All right, not fMRI here. fMRI has great spatial resolution but poor temporal resolution. EEG gives us great temporal resolution with poor spatial resolution. So here's an EEG cap. All those little blue capped discs there are electrodes that are going to measure electrical activity beneath the scalp there. So hopefully what they'll pick up is nerve cell activity. And I think that they do. So here's the data that hopefully convinces you that what we see in an EEG lines up pretty well with nerve cell activity. I'd like you to focus on the bottom portion of this illustration here. What we have down here are action potentials. I remember that action potential is that rapid change from negative to positive membrane potentials and then back, somewhere on the order of 3 to 4 milliseconds. So each one of those vertical spikes is an action potential. So in areas where you see a whole lot more vertical spikes, that means there's a lot more action potentials. There's a lot more neuron activity. If you'll compare this to the EEG data above, you can see that we get a whole lot more squiggly up and down activity in the EEG whenever we have a greater frequency of action potentials. Okay, it's not perfect. It doesn't line up absolutely well, but it's pretty good. So right there in the center of this recording, we have an increase in the frequency of action potentials, and accordingly, we have an increase in the number of oscillations in our EEG recording. So, in this experiment, it's very simple. They put an electrode into the brain, recorded from the inside of a nerve cell, and then they also recorded the EEG above that. So from this, what we should take away is that EEG kind of picks up essentially the frequency of activity, particularly in the cortex, right near the surface. So when you have a high frequency of activity, you're going to see a higher frequency of up and down motion in the EEG. And whenever there's lower frequency, well, then we should have more stability in the EEG. Now, whenever we analyze data from the EEG, we get a few different types of what we call brain waves. And the brain wave is really just that recording from the surface electrode. All right, we call it a brain wave because, we're picking up electrical waves here from the brain. We're not getting them from individual cells. What we're doing is sampling, hopefully, a bunch of cells all at once, and we're seeing what's the underlying activity. So when you see really, really fast fluctuations at about 40 to 100 hertz, so 40 to 100 times per second that EEG is oscillating up and down, that's what we call a gamma wave. This is the highest frequency that we record in EEG, and that's because of a very active cortex. You get this when someone's concentrating. When you're alert, your cortex is still active, so you still have a pretty good frequency, 12 to 40 hertz in this case. That would be the beta waves, a little less than gamma. Less than beta, we have our alpha waves. This is when you're relaxed. You'll get a little bit of these in sleep, but this is mostly during the transition. You'll see alpha waves when you're kind of drowsy and relaxed. Sleep is going to be characterized by the last two waves here, the theta and the delta waves, the slowest of all the waves. Here you can see they're about 10 to 20 times slower than your gamma or beta waves, all right, depending on where we look. So when you hear gamma, beta, alpha, theta, delta, what we're talking about are different frequencies of brainwaves recorded from EEG. Gamma being the highest frequency and thus corresponding to the greatest degree of cortical activity, and delta being the lowest frequency and corresponding to the lowest degree of cortical activity. So let's walk through a night's sleep. In a typical night, we're going to have slow wave sleep occurring much earlier than REM. REM would be that rapid eye movement, the portion where we all dream. And slow wave sleep is the portion of sleep where we have slow brain waves, those theta and delta waves. Okay, So let's walk through this. When you're awake, you're going to have beta and gamma waves. So we'll start in that upper plot there. You can see on the x-axis, we're going later in the night. So hours are increasing. We're going to say it's an 8-hour night of sleep here. First, we go from awake to a stage 1 sleep. All right, stage 1 sleep is kind of a transition period. We're not going to be in it for very long at all. We're going to have some theta waves, so our brain waves are slowing down until we hit stage 2. Stage 2 is whenever we still have some theta, and then interspersed in there, we'll have a little bit of high frequency, what we call sleep spindles, and some very low frequency K complexes. So this is kind of a more complicated stage of sleep than stage 1. Still some theta, but now we're mixing in some little bursts of activity and some periods where activity is slowing down. So we're kind of transitioning from high frequency activity into the low frequency activity that we see in stages 3 and 4. So there's the slow wave sleep there. That's when you have your delta waves, those slowest brain waves, so the least cortical activity here. You can see they're very infrequent oscillations here. So that low frequency is telling us we're in deep sleep. All right, this is slow wave sleep. Now what you'll notice at about 1.5 hours, almost 2, we're starting to come back up from stage 4 into stage 3, and then a little after 2 we're going to come back up to stage 2, and then we hit REM sleep. So our brain activity slows down as we go from awake to stage 4, but then it ramps back up. And when we hit REM sleep, you'll see this looks an awful lot like the person's awake. You'll get your beta waves. You'll see some rapid eye movements as well. That's how it gets its name. So the eyes will dart around. And it looks very much like the brain is awake. And that's kind of because it is. It's in REM sleep that you're going to dream. After a brief period of REM, we go back down to our slow wave sleep. So you can see we're cycling back and forth. We'll hit another round of REM there at 4.5 hours or so, continue to 5 hours. Now we get down to stage 3 sleep. We don't go quite as deep. We're not going to get as slow of delta waves. We'll come back up for another round of REM. You can see the duration of REM periods is increasing. Then we only hit stage 2, then another burst of REM, and then stage 2, and then we're awake. Okay, so early on, when you look from hours 1 to 4, you'll see it's predominantly slow wave sleep, stages 3 and 4 there. When you look in the later portions of sleep, that's when it's going to be a whole lot more REM. There's where we have 3 REM sessions as opposed to only the 1 in the first 4 hours. So early on, there's a lot of slow wave sleep. And then later on, that's when we get our REM. That means that the different portions of sleep are going to kind of serve different functions because REM and slow wave sleep have different functions here. We think of REM sleep as probably important for memory function. If you interrupt REM sleep in animals, then their memory function drops off. All right, and you can do this by simply waking them every time they hit REM sleep, and you can monitor that with EEG. All right, remember, it looks very different when you look at the REM sleep down there at the bottom and compare that to the slow wave sleep. All right, a night and day difference. So in REM sleep, we're probably kind of encoding our memories to some degree. All right, again, if you disturb REM sleep, then memory function drops off. REM is where most of our dreaming occurs. And sometimes these dreams get crazy. You don't want to act out your dreams. Luckily, there are some changes in brain activity that prevent us from acting out our dreams. Down there in the brainstem in our pons and medulla, these become more active and they inhibit motor output. So even though we're dreaming that we're running away from something, we don't actually start running. The pons and medulla inhibit that motor output. There's an increase in amygdala activity. This probably creates the emotional components of the brains. And then of interest to probably at least half of us there, the genitals are going to become aroused during REM sleep. And if you're a typical 25-year-old male, you'll spend about half the night with an erection. That morning wood that accompanies some mornings is just simply leftover from the most recent REM session. So REM is kind of characterized by a lot of brain activity, but we inhibit that motor output. All right, and that's very important. Some people have issues with this and they will act out their dreams. The people they share a bed with don't enjoy it. Now, non-REM sleep is a little bit more about physical recovery. All right, this is where the brain kind of shuts down, and we can recover from that feeling of tired that we get. So this kind of refreshes us, and REM sleep is more about helping us move information into long-term memory storage. That's the idea, anyway. Now, in non-REM sleep, we don't usually have dreams, although sometimes you will. This is where you'll get a lot of sleep abnormalities, things like sleepwalking. You can't really get sleepwalking in REM sleep because remember, we have that pons and medulla inhibiting the motor output, but not in non-REM sleep. So this is where you'll find people walking and talking in their sleep, and then some younger folks will potentially wet the bed there. So we mentioned dreams. There's a question of what is the purpose of a dream? Why do we dream? Well, dreams are just constructed by our brain activity. And if your brain is active, you're going to perceive something. If there's cortical activation, you're going to perceive it. Remember those when we talked about hallucinations. Hallucinations are just simply aberrant activation of the cortex. You can think of your dreams somewhat as little nightly hallucinations. That's one view. That would be the activation synthesis theory that there's disorganized brain activity, and because of that we create these kind of wacky dreams. Other folks, like Freud, for example, thought that no, dreams are really important. They tell us about our repressed desires from that id. All right, remember there's the id, ego, and superego. The id would be your unconscious kind of crazy mind. The superego is the one who kind of keeps everything in check, and the ego would be you, the thing that's constructed when the superego represses the id. Who knows? Sounds like a bunch of garbage to me, but it's all just a philosophy at this point. It could be that we dream to help us consolidate our memories. It gives us another time to think about things, and the things that we think about tend to be whatever we're generally concerned with, or anything that we've experienced throughout the day. If you've gone through a big life change, you'll probably dream about it a few times because you're thinking about it. And so part of this dreaming might help you move that information from your current worry into your more long-term memory, where you don't forget it, but it's not on your mind all the time. Now, I mentioned the activation synthesis theory, saying that there's disorganized brain activity that produces dreams. What do we mean, disorganized brain activity? Well, normally there's a flow of information from our senses to the thalamus to the cortex. Here's the weird thing that happens during slow wave sleep or during sleep. The visual parts of the brain, that visual cortex, actually becomes active before the thalamus. So it seems like information is flowing in a reverse order. All right, that's what this information here is telling you. Blue means that something is happening after, and then the red is telling you what's happening earlier in sleep. In other words, what's happening later during wake. So if we look at the red areas, we can see that's in the back of the brain in that occipital lobe. If you look at the brain image on the right there, you'll see the occipital lobes are becoming active before the thalamus. All right, in slow wave sleep, there's this kind of reverse flow of information. So our dreams are probably to some degree hallucinations based on things going on in our life. Whatever's troubling us or whatever we've been thinking about during the day, we'll hallucinate about at night. What's the purpose? I don't know. There may very well be none. Now, some of us are lucky enough to experience what we call lucid dreams, and that's where you actually have control over your dreams. Wouldn't it be nice? The idea is that everyone could experience lucid dreams if they practice. I never tried, but Google it, see if it works for you. Whenever we record brain activity of someone having lucid dreams, what we find is that compared to other people having normal dreams that they don't control, there's an increased activity in the frontal cortex. What we're looking at here is brain activity measured by EEG. Red is showing you more activity, blue is showing you less. I want to draw your attention to the very front of this person's head. So if you look at the images on the left, look toward the top. If you look at the images on the right, look just above his eyes there. You'll see there's a whole lot of activity in the people who are having lucid dreams right in the frontal cortex. So they're able to organize plans about what the dream will actually involve because they can activate their frontal lobes. So they now have conscious control during this minimally conscious state. Pretty nifty. It's hard to believe since I haven't experienced one, but I'll take them at their word. So by increasing the activity in their frontal lobes, they're able to have then conscious control over the content of their dreams. Again, this is pointing toward the frontal lobes as being a very important seat of our consciousness. Those of us who dream the normal way, with the frontal lobes having minimal activity, have no control over the dreams, and instead we're just sort of passive viewers of these nightly hallucinations. All right, you know what to do. Go ahead and pause this and we'll answer these questions shortly. All right, let's talk brain waves. So in EEG, in electroencephalography, what we're doing are putting electrodes on the surface of the scalp. We're going to measure through the hair, through the scalp, through the skull, through the layers of fluid and membrane, and try and pick up the electrical activity going on in the underlying nerve cells. So depending on how active those nerve cells are, we're going to pick up different fluctuations with our EEG. Whenever we have very active nerve cells, we're going to see a higher frequency of activity in the EEG. And whenever the nerve cells are less active, we should have less frequent fluctuations. So of the different brain waves that we see, we have our gamma waves. Those are the highest frequency. Then beta, then alpha. These are associated with being awake. Either you're concentrating, you're alert, or you're drowsy. As you slip into sleep, then you experience the slower theta waves and the very, very slow delta waves. Theta waves would be associated with kind of stage 1 and 2 sleep, whereas the delta waves are going to be found in stage 3 and 4 in the slow wave sleep. Okay, we got REM and non-REM sleep. REM is rapid eye movement. High frequency, EEG, and dreaming. Non-REM, that's the slow wave sleep. All right, here what we're going to have are the delta waves. So the function of these, well, REM is probably involved more with memory consolidation because if you selectively disrupt REM sleep, you impair memory function. Non-REM sleep is probably more associated with the physical recovery aspect of sleep, the actual resting of the body and mind. Now, whenever we're dreaming, we don't act them out. This is a very good thing. So let's think about when we have dreams. Predominantly, it's during REM sleep. In REM sleep, we have that increased inhibitory activity of the pons and medulla there. So even if we create the idea that I want to run, the brainstem is going to say no dice. Okay, so we don't act out our dreams because we have this increase in pons and medulla activity. A lucid dream, that's a dream that you have conscious control over. So in a lucid dream, you control the content. You choose your own adventure. Right? You're not passively hallucinating anymore. Whenever someone's having a lucid dream, the biggest difference between a lucid dream and a regular old dream is that activity in the frontal cortex. So in lucid dreams, we see higher frontal cortex activity, and this probably accounts for the person's ability to control the content of the dream. That's because the frontal cortex is a very important structure in terms of consciousness. All right, let's talk about drugs and wrap it up. So psychoactive drugs, these are drugs that act on the mind, that affect mental function. And as such, they can certainly affect your consciousness, your perception, your moods. Right? There are many different types of drugs. All right, here's just a few classes. Stimulants are a very heterogeneous group here. In general, what they do is activate neurons to enhance our mood and increase energy. If you've ever had a cup of coffee or a cigarette or a bunch of cocaine, you've had a stimulant, okay? So caffeine, nicotine, cocaine, amphetamine, these are all stimulants. Some of them are worse than others, but they all do the basic activity of turning on neurons. Depressants are the counterpoint to stimulants. These inactivate neurons, and by doing that, they kind of calm us, and they can be used to relieve pain. The most widely used depressant would be alcohol. Remember, that's that GABA agonist. Sleeping pills are also depressants as well. That's why you don't want to mix alcohol and sleeping pills because you're going to have too much of a depressant. And if you inactivate your neurons too completely, then you stop doing relatively important tasks like breathing. Opioids are a class of drugs that are used to help reduce pain. Okay, morphine, for example. Heroin is another opioid that's used. What these do is inactivate our nociceptive neurons. Remember, the nociceptors are the ones that sense pain. And so if you turn off your nociceptive neurons, you can still feel things, you just don't feel pain. Now, these opioids also act on other neurons besides nociceptive neurons. So they can slow down bodily functions like digestion because they'll act on our autonomic nervous system as well. Then there's the hallucinogens. These are drugs that are going to alter our mood. They can induce cortical activity to create hallucinations, and they do this in a couple of ways. Some of them are serotonin agonists. So they activate serotonin receptors, and then some of them are glutamate antagonists. So they inactivate glutamate receptors. Remember, glutamate's that principal excitatory neurotransmitter. All right, and so what these do is essentially turn off some of the control that our brain has, and so that's how we'll create hallucinations there with PCP and ketamine. But these are very dangerous compounds. If you take ketamine, this can induce paralysis at higher doses. That paralysis can also include the nerves and muscles that control your breathing. LSD and psilocybin from magic mushrooms, these are serotonin agonists. So by just directly activating serotonin receptors, they can create that cortical activity that then generates hallucinations. Cannabinoids, I put in their own class. Sometimes people will put THC as a hallucinogen. They've clearly never done any THC because they know this is not a hallucinogen. This definitely alters moods, but it's not going to induce cortical activity. You should not hallucinate on THC alone. If you are, something is very wrong. But what it does do is impair memory function. And it does this by cutting down neurotransmitter release. So it's a completely different mechanism of action. So it should be its own drug. It's not a hallucinogen. This is not an agonist or antagonist. This simply reduces neurotransmitter release probability. As such, whenever you try to activate a synapse to help you remember something, well, then the presynaptic site doesn't function well, and that memory just doesn't come to your conscious awareness. So that's how we can impair memory function at a very basic level. Now, when you hear about drugs, you always hear drugs are bad, and that's because they're addictive, and some of them are very addictive. And when they are, this is definitely a bad thing. Now, drug addiction is totally a natural homeostatic response. Okay? This is, again, homeostasis. You can't escape it. Don't try. Bad things happen when you try to escape homeostasis. So let's see this very basic example here. The plot on the bottom is showing you dopamine signaling over time. All right, dopamine is very important. That's what determines our reward, what makes us happy, if you will. We got ourselves a blue neuron there that's going to respond to dopamine and make us happy. All right, this is a neuron, let's say, in the nucleus accumbens or something like that. We'll talk about that in just a moment. So when you see a kitten, This is going to activate your dopamine neurons if you think kittens are cute. It'll release a little dopamine and we'll say, oh man, what a cute kitten. It's a lovely thing. All right, that's early on. This is before we've gone out and experimented. And, maybe you do some cocaine and you have a look at the same kitten. Well, now, there's essentially the same amount of dopamine, but we prevent the release, so we got a whole lot of dopamine floating around. So that same neuron now is experiencing a whole lot more dopamine on it, and it says, man, I'm really happy that kitten is there. But all things come to an end. When you're off cocaine, that nerve cell is going to respond because it had so much dopamine signaling going on. Homeostasis has caused it to remove some dopamine receptors. So when you look at the kitten, you get normal dopamine release. Because that neuron is downregulated its dopamine receptors, the amount of dopamine signaling in that neuron isn't high enough to make us happy. And now we look at the kitten or whatever else is in our life, and it just doesn't make us as happy. Not without that cocaine there. All right, and this is kind of a big reason why we're going to develop drug addiction here. So let's walk through the cycle. First, we have an increase in tolerance. Okay, prolonged receptor stimulation is going to cause downregulation of the receptor. No doubt about it. It's just simple homeostasis. So you snort a whole bunch of cocaine, you're going to flood your dopamine receptors with dopamine because we're no longer taking it up. If you don't remember this, see lecture 3. When we hyperactivate our dopamine receptors, the only natural response a neuron has is to start to remove some of those dopamine receptors. So now whenever dopamine levels return to normal, because we have fewer receptors, dopamine signaling becomes low. We don't feel as good. So now we become dependent on that new drug that we're taking. The high that we experience becomes our new normal. Sometimes it's just a psychological dependence, and sometimes it's an absolute physical dependence in things like opioids, where when you come off the drug, you start to experience withdrawal, these negative experiences associated with stopping the drug use. So you can have physical sickness and pain associated with stopping opioid use. And so once you've hit that stage where you're at withdrawal or dependence, you are addicted. Now, anything that futzes with dopamine signaling is especially addictive. Let's have a look at some data here rather than cartoons and kittens. Kittens are great, but we really care about the data here, right? We should be young scientists, so let's have a look at the data. What we're looking at here are PET scans showing you the ability of a compound, a radioactive compound, to bind to dopamine receptors. So when you have more signal, that means that there's more dopamine receptors there. All right, so we got control brains on the left and then drug user brains on the right. The redder the signal, the more receptors that we picked up. So in control patients, we see nice bright red signals in this area. It looks like it's in their striatum. It probably includes their nucleus accumbens as well. So a whole lot of dopamine receptors. But when you do cocaine or methamphetamine, same basic mechanism of action. Meth blocks dopamine uptake and also stimulates release. What we notice is that there's lower levels of dopamine receptors in the cocaine and meth abusers. That's because they flooded their brain, or they flooded those synapses, I should say, with dopamine by blocking uptake using cocaine or meth. The natural response of nerve cells is to remove dopamine receptors if there's too much dopamine around, and that leaves them with chronically lower dopamine receptor levels. So now when they're not on drugs, because they have lower dopamine receptor levels, they feel like shit. Their new normal feeling is whenever they're on the drug, so now they've become dependent on this. So, I'm not going to say don't do drugs because you're an adult. You can make your own decisions, but you might think twice about doing drugs that directly activate dopamine signaling. Those are highly addictive. Definitely not a good idea. Those highly addictive compounds are the ones that act on dopamine. So stimulants can definitely be addictive. People get addicted to cigarettes all the time. That's because nicotine stimulates dopamine neurons. Yeah, it doesn't affect the uptake of dopamine. Instead, what it does is directly activate dopamine neurons. So you're dumping more dopamine. And you're saying, man, smoking is great. I love smoking. I should definitely smoke more. Cocaine, on the other hand, inhibits dopamine reuptake. So we release the same amount, but it stays around. So you say, man, cocaine is great. I love cocaine. I should do some more cocaine. Yeah. And that's because dopamine is acting on this area called the nucleus accumbens to determine reward. All right, over here in the brain diagram, we got that VTA in the center. That's your ventral tegmental area. It's a source of dopamine. Those pink lines are dopamine. The nucleus accumbens is that NA(c). Then there's the amygdala, and then there's the prefrontal cortex. So the ventral tegmental area kind of tells us whether or not something is good, and we'll do that by releasing dopamine. The prefrontal cortex will interpret this. So will the nucleus accumbens, and it's really at the nucleus accumbens that we're going to determine that reward. The amygdala is going to kind of help, but that will kind of determine the negative. So whenever we don't have dopamine, then the amygdala will say, well, that sucks. So whenever we have dopamine release, the accumbens gets activated, and we say, this is a good thing. All right, so things like reproducing or having fatty foods causes dopamine release, so that we do that more often because, well, we need to reproduce so our species survives. And fatty foods are rich in energy, and so those are good to eat if you're thinking about living in the wild. You want the fatty foods. Nowadays, not so much, but that's a different topic here. So the amount of dopamine release is going to determine the likelihood of repeating an action, in other words. So if you smoke cigarettes, you have nicotine flooding your system. That nicotine directly stimulates dopamine neurons. Remember, it's a stimulant. It's going to stimulate neurons, in this case, dopamine neurons. That gives you a burst of dopamine. Your nucleus accumbens says, whatever you just did was great. You should do it again. Cocaine, same thing. We inhibit dopamine reuptake. So the natural dopamine levels present at that synapse between the VTA and the nucleus accumbens increases. The nucleus accumbens interprets this as, whatever you just did was a great idea. That's great. You should do it again. So prolonged drug use, whether it's smoking or doing cocaine or meth in this case, then lowers your dopamine receptor abundance in the nucleus accumbens. And so now, whenever you're not doing the drug, you essentially feel unrewarded. You're saying, hey, whatever you're doing right now sucks. What are you doing? Are you not smoking? Are you not doing cocaine? What the hell, man? Go do some cocaine. Go smoke. We need that dopamine. What's wrong with you? And this then leads to that kind of downward spiral of addiction at very basic levels. Then again, you're an adult. Make your own decisions. My thing, don't do anything that messes with dopamine. Okay, you know what to do. Go ahead and pause this, and in a moment, we're going to answer these questions. Okay, it's been a moment. Nucleus accumbens. That's that part of your brain that determines reward. So when the nucleus accumbens is stimulated by dopamine, we say whatever caused that dopamine release is good, and we're going to do it again. If it happened to be sex, then great. Maybe we should go have some sex again. Yeah, that'd be good. Oh, you had cheesecake? Oh, I love cheesecake. Man, it's so fatty. I got a good dopamine release. Go have another slice of cheesecake. Or, if you're full, just eat cheesecake later, but definitely bring some more cheesecake into my life. Now, because of this activity, the nucleus accumbens is then very much tied to addiction. So any drug that you're doing that increases dopamine levels in the nucleus accumbens is going to be very likely to be addictive. Because when you do that drug, you get dopamine release. The nucleus accumbens says that was great. And then if you persistently do this drug and you cause that homeostatic response, that downward, that removal of dopamine receptors, well, then when you're not doing the drug, the nucleus accumbens is saying, this sucks. We're going to need to go to some drugs, man. Come on. Now, some drugs in particular are very addictive, okay? Cocaine, for example. Very addictive stuff. And that's because it directly acts on dopamine signaling. Nicotine's pretty addictive, but it acts on actually a number of different neurons. Dopamine neurons are one of the targets, so it can be pretty addictive. But let's stick to cocaine and marijuana for the purpose of this second question here. Now, cocaine, because it's directly preventing dopamine reuptake, elevates dopamine levels in the nucleus accumbens. This says you should do some more cocaine. That was awesome. Because dopamine levels are high, dopamine receptor levels drop, and so now your normal level of dopamine seems low to dopamine neurons. And in order to get a normal level of dopamine signaling, you got to do some cocaine. Very addictive. Marijuana, on the other hand, not so much. There's no physical dependence like you'll get with opioids, and there's no psychological dependence, and that's because marijuana doesn't increase dopamine levels. What it does is lower the likelihood of neurotransmitter release. It essentially turns off nerve cells. Sure, it can brighten the mood or make you enjoy some music, but because it's not directly activating any dopamine signaling in the nucleus accumbens, you don't really get addicted to it. Certainly anything that you do every day creates a ritual in your mind, and you can certainly become addicted to marijuana, but it's difficult. I mean, you'd have to really try hard to do this. And that's because it just has a completely different mechanism of action from cocaine. It inhibits neurotransmitter release, probability, and as a result, you're not going to increase dopamine levels. You're not going to become addicted. You're not going to flood your nervous system with different neurotransmitters and cause a homeostatic downregulation of them. So as far as drug addictedness goes, marijuana is at the bottom of the list, right? The least of our concerns. Cigarettes, alcohol, and of course cocaine are far more addictive than marijuana. Okay, and then homeostasis. Can we escape it? Of course not. I know you wouldn't ask that. That's a silly question. We can't escape it, so we should understand it. So homeostasis is just trying to maintain that relatively stable internal environment. If you have too much of something, well, take steps to reduce it. If you don't have enough of something, take steps to increase it. So, prolonged heavy drug use. Well, no matter what you do, prolonged heavy drug use will cause a homeostatic response. Yes, even with marijuana. Or coffee. Hell, let's go with coffee. It's a legal drug. A lot of people drink it. Let's say you drink a lot of coffee every day. Will you develop tolerance? Yes, of course. You'll have to drink more coffee in order to get the same feeling out of it. If you smoke, you have to smoke more cigarettes to get the same feeling. Or if you're smoking opium, well, you got to smoke more of that. So that tolerance is caused by the removal of receptors. So if you drink a bunch of coffee, caffeine acts on adenosine receptors. So whenever you hyperstimulate those receptors, well, they're going to get downregulated. It's just homeostasis. It's basic biology, ladies and gentlemen. So by flooding your system with this receptor agonist, we're going to start to remove the receptors. All right. The dependence. You've probably met people who say, don't talk to me until I've had my cup of coffee in the morning. Well, that's because that new mental state that they've created, that caffeine-rich brain, that to them becomes their new norm. And part of that's because of the tolerance that they develop, because of the homeostatic response, because of the removal of some of those adenosine receptors whenever we have no caffeine in our system. Well, now we're running at a much lower level of adenosine signaling than we would have. Whenever we're not on cocaine, we're running at a much lower level of dopamine signaling. So now we're dependent on the drug to reach normal, whatever the hell that means now. And if we don't get our drugs, well, then we can experience withdrawal, some negative effects of running in this now altered state. Because we removed some receptors, the normal level of neurotransmitters just not cutting it. If you were to stop heroin use abruptly, you can experience very significant negative physical effects. Right? And that's because you've flooded your system with opioids and there's been a homeostatic response. As a result, you're going to start to feel a lot of pain, right? Because those opioid receptors are going to be downregulated. So it's all homeostasis. Right? Our cells are always trying to balance their activity. They don't want too much or too little activation. So when you do drugs, everything in moderation, and probably avoid the highly addictive substances. Anything that acts on dopamine, any of your opioids, leave those alone. Okay, that about does it for this lecture. This is the end of our first unit. We're going to review units 1 through 5, and then they will be the subject of our first exam. As always, let me know if you have any questions on this material.